Welcome everybody in the lecture hall. Welcome everybody on Zoom for one more hour of big data lecture. So I'll continue exactly where we left off yesterday in this part that I told you is going to be boring for half of you and scary for the other half. This is only a brush up. It's basically what computer scientists do during their bachelors. There is no, I would say it's not a hard requirement for the rest of the course, so you don't have to worry too much, and it's more about focusing on learning SQL. So last time, yesterday, actually, I told you about the data model, pretty simple, actually. There's tables, rows, columns, special columns that identify the rows, and then the values that are in there. So now it's nice to have tables. We have the ingredients. Now we need to do the cooking, the actual recipe. Who knows Évariste Galois? Mathematician. He was famous. He's the one who basically came up with what would lead to the groups and rings and fields and so on. So he abstracted away the notion of addition, multiplication, and so on. And so now, probably most of you know that you can also work on vector spaces. You have the inner product, the outer product, and so on. Now, what's really, really cool with relational tables is that we also have operations that we can do with relations. And it's pretty exciting. In order to do this, we need to make it a bit mathematical, so formalize a bit. And now this slide is about why it's called a relation or relational table, because actually, when you look at a table, it's a set of records. Every record is a row. And you can view it as a mathematical relation. You know that a mathematical relation is a subset of the Cartesian products of some sets. Don't be scared if that doesn't make sense, but this is the purely mathematical definition. It's basically just a set of items that we take from each domain, right? So this is the mathematical definition, but from a database perspective, even though we still call it a relation, for big data, there's better formulations than using a relation. The problem with relations is that there's no names to the columns. There's a first value, a second value, a third value. So there's a few mismatches between the math and what we want to do with the data. So instead, what we do is that we consider a record to be a map, really. So it means that if you look at the first record here, 1 Einstein, Albert, CH, it's basically a map that maps PID to 1, last to Einstein, first to Albert, and country to CH, right? So that's a map. And what we have on this slide is 6 maps, 1 for each record. And so the table is a set of maps, a set of 6 maps. For whom is that clear? Okay. So now people have different semantics. Some people consider that the order is important in which you have the records. Some other people consider you cannot have duplicates. You cannot have twice the same record. And so this is why there's a bit of freedom here. Some people say the table is a set of maps. Some people say it's a bag of maps, meaning they can repeat, but the order doesn't matter. And list of maps means they can repeat and the order matters, right? So there's a bit of freedom. Now, because I didn't see every hand raised when I asked if it was clear with the maps, so this is why I want to make it explicit. So here I took the second record, right? So 2 Ramanujan, Srinivasa, one of my favorite mathematicians. This would be the map. Look carefully. PID 2, last Ramanujan, first Srinivasa, country India. PID 2, last Ramanujan, first Srinivasa, country India, right? So this is how mathematicians would write that down. A map is a partial function from strings to values. These are non-standard. It's not like R or C, right? I just use S for strings and V for any values. Now, database people are going to lose their sanity if they need to write it down like this, right? This is really for mathematicians. So what they do instead is they use something more computer sciencey like this. Do you know what this is called, the syntax? JSON, exactly. This is JSON. Well, a JSON object is a map, right? And so you can consider, and in big data is going to be important, you can view this as a flat JSON object, right? So this is another representation. But if it's flat, you can also display it like this. So here I'm only showing that one record, right, on its own, a singleton table, right? Like this. So now it should be clear. For whom is clear? Is it clear that a table is a set of maps? Right. Okay, very good. Or a list or a bag, depending if you care about the order and everything. But there is a catch, because if you define a table as a relation, then everything will be nice. You will have the same number of values in every record and so on. The problem, if you say a table is a set of maps, that actually gives us a lot of freedom. The maps might have different supports. You might have different attributes in every map. It might be a huge mess, right? In fact, it's a feature, not a bug, because we'll see in big data, we want that. But since today I'm talking about relational tables, we do want to restrict a little bit what these sets of maps can be. And there's going to be 3 restrictions, 3. And I'm going to show them to you. First restriction, we're going to call it relational integrity. That restriction says that all the maps that are in your table must have the same support. It means the same columns, the same attribute names. You agree that these 3 maps have the same support. They all have PID, last, first, and country as attributes. You agree with that, right? This is why we can squeeze it like this as what looks like a table, because they have the same attributes. But it's best to see a counterexample. This is a counterexample. That is not, technically speaking, a table. There's holes and there's extra values like country, GB, and so on, right? So this is a counterexample where relational integrity is broken. So relational integrity, not relational integrity. For whom is that clear? Okay, that is restriction number 1, and there's 2 more to come. Second restriction is called atomic integrity. And the atomic integrity tells us something about the kind of values that we can have in our table. The values, remember, these are all what are in the cells over here, right? The scalars, the values. This respects atomic integrity. And now I don't know how to explain atomic integrity other than by giving you a counterexample. So I'm going to give you a counterexample. This is a counterexample of atomic integrity. I see a raise hand over there. That's the third restriction. That would be what we call domain integrity, right? So when we say relational integrity, it is just the attributes, just the support of the partial function of the map. We do not care. So you might have relational integrity and have a huge mess in a column where you have integers and strings and dates all mixed, right? So that is not a requirement of relational integrity. Did I answer your question? Yeah. Not just the same number, the same names too. The exact same, it's called the support of a map, right? So it's all the left-hand sides that are associated to, let me show you here. So this is, it's called, mathematicians call it an extensional definition of a function because you define it with all the values. And this is the support. It's the set of all the mathematical values in the domain that are mapped to something, right? Does it make sense? All right. So relational integrity, atomic integrity, which is broken here. Do you see the difference? The difference is that we have tables in the table. And I like to compare that to the Inception movie. Who saw the Inception movie? A dream in a dream in a dream in a dream in a dream. And so broken atomic integrity means we have a table in a table in a table in a table. Anything structured in a table, lists, arrays, anything that is not just a single value. So here we have tables in the table, so it does not respect atomic integrity, right? A table is not an atomic value. Atomic values are strings, integers, dates, and so on, single values. For whom is that clear, atomic integrity? All right, very visual, right? And the third one, which might be what you were referring to, domain integrity, it's that we look across all the records for a specific attribute, actually all of them, but one by one. What are the values associated with that attribute? They should have the same type. Here, for example, we have domain integrity. I put actually the types that we have here. These are all strings. These are all strings. These are all Booleans, true, false. And these are all integers, right? Let me show you a counterexample. Here we have a Boolean, an integer, and a Boolean. So it breaks domain integrity because we are not able to find some type or domain here. So now, people might object, yes, but what if I just take as the type of everything, right? You could always do that. I mean, mathematically, you can do that. But we are computer scientists, and what we mean with types here is not abstract types, concrete types, like strings, integers, dates, binaries, and so on, right? So it has to be a concrete type. Who agrees that here that breaks domain integrity? Awesome. Also the fourth column. In the fourth column, I'm assuming we're not using LLMs or anything that could basically fix it in any way. So 42, it's technically a string here. And so it's also broken. All right. And so when we have the conjunction of these three restrictions, relational, atomic, and domain integrity, we are in the wonderful world of relational databases. Okay? So this is also what we refer to as SQL databases, but SQL is the name of the language. So this is right here. That's where we are in today. What's really nice is that when we want to go to big data in the coming weeks, we'll just break the rules, right? We'll just drop these three restrictions and allow any sets of maps, even if it's not atomic, even if it's not the same support, even if the columns are heterogeneous. But not today. Not today. Today, we are assuming that these three restrictions are in place, and we are looking at relational tables. Now, there's a bit of theory that we do in the database courses when we teach these things. There's actually more restrictions that we want to have in addition to these three. And these restrictions are called normal forms. So when I say normal form, to whom does that ring a bell? I assume everybody who took the bachelor's lecture. Yeah. To whom does that not ring a bell? Okay. So don't be scared, because the reason I'm showing to you normal forms is because we are also going to break them. So don't worry about that. So I have first good news for you, because what we call the first normal form, you already know it's atomic integrity. It's just another name for it. We also call it the first normal form. So a table is in the first normal form if it respects atomic integrity, and if it breaks atomic integrity, then it's not in the first normal form. So that one is easy, because that's just a synonym for something that I've already explained. That's a counterexample. That table is not in the first normal form. Technically, it would not even be a table because what I explained before. So the first normal form is very important and fundamental to talk about tables. That is in the first normal form. It has atomic integrity and relational integrity and domain integrity, but the normal form is really the atomic integrity, first normal form. Okay, and then, as you might imagine, if there's a first normal form, there's also a second normal form, a third normal form, a fourth normal form, a fifth normal form, a sixth normal form, and even a 3.5 normal form, also called the Boyce code normal form. So I'm not going to throw all of them at you, because that's several weeks of teaching and difficult exercises that we do at the bachelor's level. And anyway, we're going to break them. So I'm only going to give you the intuition of what a normal form is and what it means to break a higher normal form. So what better way to understand it than to see a counterexample? This table is not in the Boyce code normal form. Here's why. If you look at it, you notice that we have here a city and a state. So you know that the city alone might be ambiguous. For example, Pfäffikon. There's one in Schwyz and there's one in Zurich, right? So we say Pfäffikon Zurich, Pfäffikon Schwyz. The same goes, there's a Zurich in the US too. There's actually probably several of them called Paris and so on. But if you take the name of the city plus the canton or the state, and we make the assumption that it identifies uniquely a city, then we have here some dependency. Do you agree that, again, if we assume a city name is unique within a state or a canton, then the city name plus the state uniquely identifies the city ID. Who agrees with that? All right, we call that a functional dependency. And that's because this can be seen as a function of this. So the city ID is a function of the city and state. So the city and state uniquely identify the city ID. Turns out database people hate this. We hate to see functional dependencies within tables like this. Why? Because it's a functional dependency not on the entire table, but just on some part of the table. We don't like this, not at all. It leads to so many problems when you want to keep the data consistent and update and so on. And so what we do to fix it, we split the table. Basically, what it means to have functional dependencies like that is that table is too big. It's doing too many things at the same time. And so being in a normal form intuitively means you have one table for each concept. For example, if you're an online shop, you have one table for the customers, one table for the items you're selling, one table for the orders, one table for the inventory, and so on and so on, right? So you have one nice separate table for every single thing. And people have come up with algorithms that take a table that is guilty of not being in a normal form, and there's an algorithm that tells you how to split it and make it a normal form, multiple tables, right? Does everybody have the intuition of that? So normal form means fewer tables that each do one thing. That's what it intuitively means. And not being in the normal form means one single big table or fewer big tables, but they do too many things. They contain too much data, and then you have these sorts of dependencies. So that's the intuition of normal forms. Okay, and again, we're going to break that so much during this semester. We are going to have plenty of data that is not in the normal form. We are going to see that when it's not in normal form and not even in the first normal form, what we get is trees, collections of trees. That's maybe one thing to remember. I have a quiz next week to ask you if you remembered what I've just said. All right, so what we have now is a relational model. Tables are sets of maps plus 3 conditions: relational integrity, atomic integrity, domain integrity. And we love it when there's normal forms, when the data is even in higher normal forms. But what do we want to do with tables? We want to manipulate them. We want to query them and extract some information from the tables. And this is why I mentioned Évariste Galois, because we have what's called the relational algebra, which is a set of mathematical operations that take tables and return tables. It's beautiful. And we're in Switzerland, so I nicely sorted it into buckets like this, all tidy. So we have set queries, the union of tables, intersection of tables, subtraction of tables. A table is a set of maps, right? So we can do that. We can filter on tables. I have a few slides. We can rename the attributes, rename the tables. We can group, we can sort. If it's a list of maps, then we can change the order. And we have joining queries where we take several tables and put them into a larger table. That's called a join. We'll see they're very expensive, and in big data, we are a bit scared of this. All right. So I said I have a few slides for the most important ones. I'm pretty sure everybody uses a spreadsheet, right? Everybody is familiar with spreadsheets. So what's nice is that even if you've never seen the relational algebra before, that's all things you've done in a spreadsheet. So if you activate the data filters in the spreadsheets, then you can filter on some records. That's called a selection. You select some of the rows that satisfy some predicates. In that case, I took the predicate country is GB. So in a spreadsheet, you can click here and say GB, and then it's going to select just these two. That's called a selection. A projection is when you pick a subset of the attributes of the columns. So here, if I only want to keep last and first, and I hide the rest, so you can, in a spreadsheet software, you can hide it, then you just keep last and first. So selection, projection. They're kind of dual to each other in the sense that one does it on the rows and the other one on the columns. Everybody's with me? Right? Even people who didn't follow a database lecture on the bachelor level. Okay. Then we have grouping. This is what people in statistics offices, like the Federal Office for Statistics, they love to do. you have basically an enormous table right here, maybe all the population of Switzerland or all the populations in the cities, and you want to aggregate them by canton. And so what you do is that you notice that there's values that repeat here, and you want to group them. 19, 4, and 46, you want to add it to 69. Bar, this plus this plus this plus this adds to this, and so on, right? You know foobar, where it comes from. The computer scientists call everything foobar when they don't know what to. It's Furchtbar. That actually comes from German. Anyway, so I just put there because I had no imagination. This is a grouping where you notice there's 3 unique values. And in the output, you have each one of these unique values plus some aggregation. So here it's addition. You could also use max, min, count. There's many ways you can aggregate. Standard deviation, anything. So that's grouping. And sorting is when you keep the same records, but you just reorganize the order in which they are shown. You can do it ascending, descending, multiple columns, also first, second, third column. Again, all things you do in spreadsheet software. Something else you can do with tables, and that in data scares us even more than the joins, is the Cartesian product. You can, because these are sets, right? It's a set of maps, it's a set of maps, so you can take the Cartesian product of this, and you get a bigger table where basically every combination of one record here and one record there. The reason we are scared is, do the math. We'll have tables in this course that have, let's say, 1 billion records in here, and other tables that have 1 billion records in there. The table that is the Cartesian product is going to have how many records? 1 quintillion. That is going to break the data center. So I don't know if it will collapse or anything, but this is really beyond the boundaries of what we can do. In fact, it is such a big deal that by default in Spark, it's deactivated. It will not even let you compute Cartesian products until you activate the feature of Cartesian product. So instead, we prefer to join. It means that we don't take all the combinations. We only take those that match. For example, 1 will be associated just with 1 here, in here, and 2 will be associated just with 2 here, right? And so now we join. You see the link with the normal forms? Because technically, we might have a database, so tables in normal form. When we join them, we get a table that is no longer in the Boyce code normal form, right? So there's this notion of normalization, denormalization, right? So to draw some parallel. For whom is that clear? Right? Awesome. I don't know why it's on track. This was supposed to be a quiz question, and it doesn't even display. I don't know. I look at it, but maybe I can ask you. Who has never ever heard of SQL, except maybe that I said it here, but who's never heard of SQL before? SQL. Okay. Who knows a bit of SQL? Maybe you did a website or something and you've written a few SQL queries, but not more than that. Okay. Who is very familiar with SQL maybe from the bachelor's database lecture? Okay. Who knows by heart all the way to the 6th normal form and programs video games with SQL? Usually there's 1 or 2. Yeah. And the video games with SQL is not a joke. There's actually a professor at Cornell. I remember he gave a talk a few years ago. He was looking at, you know, these real-time strategy games, right? Like the Settlers or Red Alert, or who remembers these games, right? This is actually a database problem. And he showed this is a database update problem. So whenever you modify something, you're actually updating the underlying database that contains the state of the game. But anyway, that's as expected, a distribution. Some of you are very familiar with it, some less. And that's okay. So let me give you the landscape of languages in general. In the very early days of computers, we had to be very low level, directly at the level of the chips and CPUs. And then some people invented languages. BASIC was one of the first, COBOL, Fortran, and so on. Now we have C, we have, since the 90s, Java, we have C++, I think from the 80s, we have R, we have Python now today, and so on. So this is much higher level. But it's still software engineering because you're telling the computer what to do. In databases, we also have 2 levels. We have the API level, and we are going to look a little bit in the APIs. An API allows you to manipulate the data, with some, it means application programming interface. So you manipulate the data explicitly, but then you also have higher languages, and that would be the role of Java and the others here, like SQL, Sparkle, JSONic, Cypher, and so on. There's many languages that are, it's much easier to use a language like that than to make API calls on the data. And that I will show you during the lecture. Then we have machine learning, totally out of scope, but it's the same idea. You have frameworks like TensorFlow or PyTorch that allow you to use an API to do some machine learning. And there are people actively trying to come up with declarative languages on the high level to do machine learning so that you don't have to worry with making complex API calls for machine learning. So that's the landscape. And in this course, we are going to focus on this, right? The database landscape. So now, a few words about SQL. So the initial ideas came from Edgar Code, right? The idea of data independence and manipulating tables. And then very quickly, a lot of people started thinking about these things and how can we build a system that actually implements Edgar Code's ideas. And so some of the first people to do that after Edgar Code were Don Chamberlain and Raymond Boyce. Boyce, by the way, Boyce Code normal form, that's him. That's his name in the Boyce Code normal form, right? He was at IBM. So in the early 70s, that was more than 50 years ago, in Almadon, in San Jose, in California, it actually still exists. The laboratory is still there. You just need to traverse a bit of desert with a car in order to get there, but it's still there. And they came up with a commercially usable system called System R and a language called SQL, written like this, that also was supposed to be the first commercial relational query language. And their first customer, it took a few years, right? That's already 1977, was Pratt & Whitney. That was the first customer to use the database. And so some other companies were created, software development laboratories, now known as Oracle. I mentioned it yesterday. And now we have basically the big three are Oracle, IBM, and Microsoft. SAP is often added, especially when you go in the context of business analytics. But this is basically the, I would say, the relational database markets. I'm not mentioning yet Databricks, Snowflakes, and so on, because they came later, right? So this is big data, NoSQL, and so on. All right. But then you might have a surprise if you saw SQL written like that. You might be wondering, why did you write SQL like that? Because it was the original name. But then they got a trademark lawsuit. And so they couldn't keep that name because it was already in use. It was supposed to mean structured English query language. It was supposed to be as easy as writing English. And so they renamed it to SQL. But many of the people continue to say SQL. I'm guilty of that. I also say SQL. I'm influenced by some people who say SQL. And so that's how I say it. But it's the same. SQL, SQL, it's really the same. Just out of curiosity, who here says SQL? Okay, who here says SQL? Right, so we see some influence as well. All right, maybe after the course, more of you will say SQL because of me, but we'll see. All right, SQL, SQL. So what's particular with SQL is that it's declarative. Declarative is the difference between cooking at home, where you do all the recipe yourself, or going to the Mensa and asking for the veggie menu. Right, so this is the difference. If you just ask for the menu, you're basically declaratively ordering your food. And if you do the recipe step by step, you're imperatively cooking, right? So C++, Java, Python would be imperative languages. SQL would be a declarative language. So it means that you just logically say what you want, projection, selection, and so on. And the details of the executions, you don't care about them. Why? Because some people took care of it for you, right? So the people who built Oracle, IBM, Microsoft database systems, they implemented the physical execution, right? So this is what's important about the declarative language. You don't need to worry about how it's done, only what you want. And one of the aspects of this is that you can also parallelize, and we are going to parallelize a lot in this lecture, but it doesn't change the query language. And now that might ring a bell, because when's the last time I showed you something that changed at the bottom and that remained unchanged at the top? That was data in dependence, exactly. And that's the same idea of data independence. You have a logical language on a logical model, tables, and you can change the physical layer all you want. The user won't notice a difference, except that maybe that it's faster. All right, SQL is also a functional language because you can nest expressions within each other. I'm going to show you a few examples of that. That is a feature of functional languages. It's basically a language that feels a bit mathematical in the way that it nicely composes. It's like a Lego game. We'll have plenty of opportunities to look at languages like that. And so my request to you is to brush up SQL or to learn SQL. The TAs are going to prepare exercise sheets for you, and you will be able to learn it. That's an example of SQL. See, select star everything from persons where last name equals Crusher. That is a selection. It selects, persons is the name of the table. Last name equals Crusher. It's going to select here this row over here. Right? You might have recognized Star Trek characters, Beverly Crusher. Anyway, this is a selection done in SQL. This is a projection done with SQL, where you have here the name of the columns that you want to keep, and it's keeping these two columns, right? So this is SQL, and actually, this here is the most general view of a SQL expression. You should learn the order by heart because it's actually a strict order. You cannot shuffle that around in a different order. So it has to be select from where, group by, having order by, limit of set. You will learn in the exercises to do it. Some are optional, so you can omit any of these, except maybe the select and the from, but the others you can omit. But it has to be in this order. You cannot have having before group by or anything like that, right? For whom is that clear? Right? And you will learn that in the exercises. You will write a lot of queries like that interactively and see what it does in your notebook, right? Another example here is how you do grouping. With a group by clause, you can aggregate. That's the example I showed you earlier about the statistics office. Here you can count how many people per century, 23rd and 24th century, 2 of each, right? So this is an example of group by query, right? And you see the order, select from group by, select from group by. That's in the right order. Then you can join. It's all because it's a declarative language, so it really doesn't take much to do that. You can have a join between the two tables. It's a natural full outer join. What does that mean? It's not to scare you. Natural join just means that you look at the attributes names that are the same. There's the same attributes, last name, on both tables. So a natural join means that you use this to do the matching. Kirk, twice. Crusher doesn't have any correspondence. Janeway here. Picard doesn't have any correspondence. And full outer means that those that don't have any correspondence, you still put them in the output, but you put nulls everywhere else, just because you don't know the value. Right. I'll come back in this lecture on the semantics of nulls and so on, but you can see them as absent values. And yes, you could argue that breaks relational integrity to have nulls or missing values. All right. And since I said that it's a functional language, I have to give you an example of an expression. It's inception again, right? An expression in an expression in an expression in an expression. And so you can, in SQL, put a select from where inside a select from where, right? And even multiple levels of that. So that's an example where we have a select from where, select from query, and we put it inside the from clause of another query, right? So again, brush up on your SQL. If you don't know SQL and this is new to you, just take the time to do the exercises and learn it step by step. You will see it's a very pleasant language to learn. And it's so interactive in the Jupyter notebooks that it's even a pleasure to do this, because you type the query, you press the button, and you see the results immediately displayed on your screen. It's very pleasant. All right. What's good to know too, and that's general knowledge, is that because it's a declarative language, it requires a physical implementation. So there is going to have to be some data and bits that moves around in the computer to compute the results of your query without you needing to worry about it. And the way it's done, again, without the user knowing, is that the system is going to create what's called a query plan. It's going to find the best possible strategy to execute the query. And in the theory, we love to use Greek letters for the relational algebra. So we use sigma for the selection, we use gamma for the grouping, again, sigma for the selection. Having is actually also a selection, but of a group. And select, we use pi for projection, right? So the Greek letters, just don't be surprised, this is for the relational algebra in the query plan. And so the beauty of it is that the system, PostgreSQL or Oracle or IBM, is going to figure out the best query plan that it can come up with, and then it's going to execute your query and give you the results according to the best query plan that it's found. Okay? Any questions so far? Is everybody following? Yeah, all right. Now there is something important to help make the queries fast. Because if I give you a table with 1 trillion entries in there, and that actually exists, and I ask you to locate a specific entry, a specific record, well, at first sight, you would have to look everywhere, a full scan of the entire table to look for what you're looking for, right? But we can actually do this in just 2 milliseconds. How can I locate in just 2 milliseconds or a few milliseconds a specific record in an absolutely huge table? The secret is called an index. And an index is what you have at the end of a book. You've seen alphabetical lists of words, right, at the end of a book, and you can very quickly locate the pages on which the words appear. You've all seen that, right? That's an index. And database systems do that. So when you have a PostgreSQL or Oracle, any system, they will build index structures like this automatically. You don't have to worry about it. You just can request the index, and that's it. And then the query will be just faster, much, much, much faster. So that's the magic of indices. I'll show them to you in the framework of document stores, the hash indices, B+3 indices. They are very similar to those you saw in relational databases. Okay? The next point, all high level right now, right? All high level. The next point I want to discuss is that when you have a database, what do you do on a database? You read the data and you write the data, right? So you can just read it or you can modify what's in there. It turns out that it's important to ask yourself when you want to use a database if you want to read or if you want to write, what you want to do the most, because that actually decides on what system to use. If you have a web shop and the customers place orders and the inventory changes the whole day and it keeps being updated, then you have a write-intensive system. And that's the fancy word for that is OLTP, online transaction processing. Think a shop like Digitec Galaxus or anything like this. This is OLTP. You have a system that just keeps updating the data. And here you want your data to be in normal forms for when you have these updates. But there are other use cases where you just want to analyze the data. You don't want to modify it. You just analyze it. That's called OLAP, online analytical processing. Turns out that many of the systems we'll see in this lecture, like Spark, MapReduce, are a bit more on the OLAP side in the sense of being read intensive. What's really cool is that this is why we can break the normal forms. Because here we don't care about normal forms anymore. We read the data. We don't need to worry about the problems that would arise from not having a normal form. So you need to ask yourself, am I write intensive or read intensive? Because that actually decides what kind of system you're going to use. We'll see a bit of both in this lecture. I'm almost finished showing you the very high level takeaway messages. What do we have also in a good old relational database system from the 70s? Well, you probably know if you use the system to order from an online shop or you book a train ticket, you're not the only one using the website. There's probably thousands or millions of other people using the website. So now you have to imagine that database system with millions of people updating it and placing orders and modifying it. You realize that it should not crash. It should actually be able to sustain that, millions of people at the same time. And so there was a bit of theory and actually implementation done in order to make systems like this work, even with millions of people using them at the same time. And so the concepts are atomicity, consistency, isolation, and durability. To remember them, it's ACID, A-C-I-D. Atomicity means that whenever somebody interacts with the system with multiple queries, it's all or nothing. Concrete example, imagine you go to the ATM and you ask for a few banknotes and it says, oh yes, it's been deducted from your account, and then there's no banknotes that come out of the ATM. That's a problem, right? That's an example of non-atomicity in the transactions, right? Either you want the banknotes in your hand and it's been deducted from your account, or you don't have the banknotes, but you do not want it to be deducted from the accounts. All or nothing. That's atomicity. For whom is that clear? Atomicity? All right. Not to be confused with atomic integrity. These are two different things, right? Atomicity. The second one, ACID, C. Consistency means the database is always in a consistent state. For example, when you have a bank account, that bank account must be associated with a person that exists, and that's also in the database. That's an example of consistency, right? And so you can define what it means for your database to be consistent. A system like PostgreSQL or MySQL and so on can ensure consistency, and if at any point you try to do something that breaks the consistency, it's going to complain and it's going to throw an error. So that's one other benefit of a system like that. Another example of consistency is that you don't have two people who booked the same seats. Now, I know in practice that's not how it works. You do have overbooking, but imagine that it's enforced, then you should not have two people who booked the same seats. That's another example of consistency. Okay? All right. But the reason it's done is not because of databases that can't do it. It's just an economic decision, not a database decision. All right. Consistency. Isolation means that when you're booking your train ticket, it should feel to you as if you were the only person in the world booking your train tickets. You shouldn't see any interferences with other people, right? So you get your seat is blocked and so on, and you don't see the seat suddenly disappear because somebody else booked it, right? It's kind of blocked for you. So that's isolation. The system is behaving in such a way that it makes you feel like you're the only one using it. Isolation, even though there's millions of people. And finally, D, durability. Once you have booked your seat and paid for it, you don't want the booking to disappear. You want it to be durable, right? It has to be in the system and stay in the system. Even if you shut the machines down or there's an electricity shortage or something, it has to stay. The data has to stay. This is durability, right? So atomicity, consistency, isolation, durability. It's very, very difficult to implement. This is why these pieces of software are so complex to build. And in fact, it's so complex that in big data, it took us 20 years to start being able to build systems with trillions of records that do that. And now we are in times that it's slowly coming. Even a few years ago, I was saying that doesn't exist in big data, but this is coming. Now we are starting to see this also in big data systems. Very slowly, it's taking time. Okay. So we are going to see in the semester, because next week we are actually going to start looking at the material and cover things. What we will see, we'll see systems with lots of rows, trillions of rows, billions, trillions of rows. We'll see systems with lots of columns, much more than what relational databases can do, typically 255. We can have millions or billions of columns. And we'll see inception, lots of nesting, tables in tables in tables in tables, because we are going to break normal forms and the rules of SQL. All right. Who is with me and understood what I've told you today? All right, very good. So this is it for today. Thank you very much. I'll see you next week at 2 p.m. in the other room. Thank you, goodbye.